So let's talk about what I consider the more interesting organic molecules, and yes, that's my editorial there. We're going to talk about peptides, specifically the amino acids. Now, polypeptides are composed of multiple amino acid units, or polypeptides are considered composed of multiple peptides, and we're going to use peptides and amino acids here synonymously. So, first of all, let's talk about what they are. Well, the acid here is going to refer to the carboxylic acid group on the compound. The amino, so amino acid here, is going to refer to an NH2 group. So we have both an amine and a carboxylic acid. And we can name them based on, or classify them based on the position of this amine. So if the amine is on the first carbon, this is what's considered an alpha amino acid. If it's on the second carbon, this is what's considered a beta amino acid. And for successively longer chains and further away, we have gamma, delta, and so forth. So what's one way at looking at these is basically the position of the amino acid. Now, if we have an alpha amino acid, so the one over here, that DL that we used for sugars, so if the aminos on the amines on the right versus the left, that's still going to hold here. So in this case, this is D, whatever this amine is, and L if it's on the other side. Now, what I find most interesting about amino acids is that we actually have two groups here. We have the carboxylic acid, which as the name implies is an acid, and we have the amine here, which is a base. So you have two groups on this compound that actually work for opposite means. So if we were just to put this compound in water, so just add it to water, we would never get this form. This is a nice way to draw it, but it's not really true. We'd actually get, we look at pH, and let's say we titrate it. Well, when we just put it into water, the water here, the amine here is going to act as a good base. And so we're going to end up getting, oops, drew it the wrong way. The NH3+. Now, as we start adding more base to it, we're going to start deprotonating, but we're not actually going to deprotonate the amine. What we're going to do is we're going to deprotonate the carboxylic acid. So here we have just purely positive, here we have a negative positive, so this ends up being an overall neutral molecule, and this is what's considered the isoelectronic or isoionic form of this compound. And finally, when we go to low enough pHs, we get rid of the protonation of the amine group and we end up with just the negative carboxylate ion. So what does this look like for a titration curve? Well, when we first add it in, this is the complex we get. And we'll get our first weak acid titration curve as we start pulling the proton off of this carboxylic acid. And at some intermediate pH, we get the isoelectronic or isoionic form of the complex. Then as we go to higher and higher pH, we begin to remove that proton from the amine, and we'll actually get what looks like a second weak acid titration. So we have our first weak acid, the Ka1, and this is your carboxylic acid. Your second weak acid titration, your Ka2, which is associated with deprotonating this amine, and halfway between the final titration of this form and your starting pH, this is the pH at which you have your isoelectronic point. So this is, for me, the kind of cool thing about amino acids, that they do actually contain both an acid and a base functionality. We're able to generate Zwitterions doing this, that we actually get both a positive and negative at the isoelectronic point. Because when we say isoelectronic, we mean zero overall charge. And clearly we have two separated charges here. We have the carboxylate ion and we have the ammonium ion. It's not until we go to really basic conditions do we actually end up getting rid of this protonated amine form. So that's pretty much amines and peptides in a nutshell.